Oh, you're recording. Why? No, we're recording. Well, okay. Queen is recording the call. Okay. Good morning, Queen. You always is coming early, right? Yes. Cesar, how's it going? Good morning, Lustin. Banks, amazing. Car Bolivar, Fran Lopez, and I don't remember your name is your nickname. I don't remember. You could is Jasmine. It's a beautiful name. Jasmine is a beautiful name. Okay. Andreina Hernandez, good morning. Let me ask a question. Do you see the whiteboard now? Or no? Do you see whiteboard? Yes, okay. Jasmine. Let's wait in 2 minutes to start. This is the topic we start today. Rational functions. Good morning, Randy. Good morning, Jennifer Torresillas. Randy, do you hear me? Yes or no? Randy? Okay. Okay, ready. Okay. Do you see whiteboard, right? Okay. So we start. We start. New topic. Are you ready to pay attention? Yes or no? Come on. Okay. Yancy Maria. Okay. Definition first. Definition is a rational function is a function. Is the division to polynomial. P divided by Q. And of course, P and Q are polynomial function, exactly the same we studied last time. Are polynomial, any polynomial. Doesn't matter the degree, function. The only restriction, of course, is that Q should be not zero, because undefined, division by zero is undefined. This is the definition. Okay, and this create a new complication that we are studying now. Different situation, very, very different to the polynomial, because polynomial is super nice. For example, the polynomial domain, you remember very well, gets all real number. And the rational, no, because we have division, no? When the division, we have restriction. Maybe the most common case is that we have restriction. Sometimes no, but sometimes yes. Okay, I bring a picture to illustrate one thing. For example, you have functions, rational function. We are talking about rational functions. I present 1, 2, 3, 4 example. This now I present in factory form, factory form. And also I want to investigate, well, as always, domain to see that no always is a real number. No. We have another combination. No? Okay, the first example, elementary, is f of x equal 1 over x. And 1 over x is a reciprocal function. And the factor 4 is exactly the same, because in this case, the rational function is formed by, in the top, is a monomial degree 0 because it's constant, and the bottom is a monomial also, degree 1. Okay, so it's impossible to do something more extra to the factor 4. And the domain is obvious, it's all real number except 0. So we can write like that, it's x value such that x not 0, because the denominator expression is not 0. Okay, this is one way to represent this idea. Or another way to represent the same idea gets equivalent using another notation is parenthesis from negative infinity, comma 0, parenthesis union 0, comma infinity. So basically, see, we are doing the graph, it's all real number. This is all real number, look at that. And in 0, we have a hole. A hole is empty, a hole. We have a hole. Okay, this is a symbolic way to represent a hole in one dimension. It's all real number except 0, because 0 ought to be undefined. No? 1 over 0 is undefined. Okay, super. This is my first elementary example. My second is a little bit more interesting. Suppose the function g, and the top we have monomial, degree 2. And the bottom we have trinomial, degree 2. Okay, let's do it in the factory form. G of x is equal 1. The only thing you should do is factorization. Factorization at the top, when it's a monomial, stay the same. Factorization at the bottom was trinomial, open 2 parentheses, because I know that the factorization 1 trinomial is 2 binomial, and the combination in that case is 3 and 2, negative both. It's a factor form. Okay, now the domain is obvious, it's all real number except the bad guy, the restriction is 3 and 2, no? Because you evaluate the function. So you evaluate the function, this function, and 2. Or you evaluate in 3. We have 0 in the denominator. 3 minus 3 is 0, or 2 minus 2 is 0. So in both cases, to be undefined. Okay, undefined is totally outside the domain to say I can write the domain like an all real number except 3 and 2, no? Entonces es all real number. So X, you open this curly bracket such that no 2 and no 3. If you want to represent the same idea in interval notation, basically we have 2 holes. Look, this is the sketch in 1 dimension. Infinity positive, infinity negative. And we have 1 hole in 2, another hole in 3. So our domain is from negative infinity to 2. Do not include 2, and between 2 and 3, from 3 to infinity, don't include 3, of course. And the answer in the other notation is equivalent to say another way to present the same idea is from negative infinity, comma 2, union 2, comma 3, union 3, comma infinity, because we have 3 interval notation. Everyone follow me? It's clear, it's easy. Nothing is new, eh? But the most important, clear, super. The most important is this new function that we are studying, the name is rational function. It's a little bit more complicated because the domain is no all real number like a polynomial. It's super nice. In this case, very, very picky, very, very sophisticated, very, very complicated function. And sometimes we have a function. And the most important, the steps number 0 to start any problem in the analysis of the rational function is expressed in factory form. The factorization, the polynomial on the top, factorization, the polynomial on the bottom. This is the first step to analyze a rational function. Okay, I bring another example. Suppose h of x is equal x plus 3, it's a binomial in the top, and the bottom is also binomial, but degree 2. So in the top, we have binomial degree 1, linear, and the bottom, we have binomial again, 2 term, degree 2, it's quadratic. And the factory form, in the factory form, well, this binomial stays the same, it's obvious, right? But this binomial is impossible. It's irreducible. Quadratic expression. Quadratic expression. How do you know that? Well, because I am familiar. Expression. I am familiar, super familiar when I study factorization. No? The binomial difference of a square. The factorization is a plus b, a minus b. This is a classic formula of the factorization. But when it's plus, this expression is prime. The reason que es prime is because the solution, for example, so I try to set up this equation. I force it to be 0. Okay, the bottom expression equal to 0. I try to solve it. I move forward to the right-hand side, apply square root both sides, the classic square root method, x is equal plus or minus, and square root negative 4 is 2i. Now, so when this imaginary or complex, remember, this restriction you try to find, but you discover it's imaginary or complex because in the real field do not exist. By the way, this is suppose that I try to do the factorization for this. Well, the factorization of this is similar, is a plus ib, a minus ib. That is a reason that in the real field we consider that this sum of a square is irreducible quadratic expression in the real field. We can factorization in the imaginary or complex. Yeah, we can, but this is not important for me now in the real field. So what is the super fantastic conclusion about domain? What is the domain in your opinion? Domain is the value in which the denominator expression is 0. And we discovered that it's plus or minus 2i. It's imaginary. Therefore, in the real field, we have no restriction. Now, the domain of this is all real number. Domain is all real number from negative infinity to positive infinity, like a polynomial. Unbelievable, but it's true. When you have in the bottom irrational expression, irrational quadratic expression, is the domain is all real number. Did everyone follow me? Something weird, something confusing, something that you need to clarify? No, it's easy, right? Okay. I have another example, very important. In my opinion, the most important example is number 4. And number 4, the name of the function is p of x is equal x minus 3 over x squared minus 5x plus 6. I copy the same trinomial because I don't want to complicate with the factorization. This is not my problem now. And when you write in factor form, well, the polynomial on the top, okay, degree 1, stay the same. The polynomial at the bottom, the factorization is exactly the same idea here. X minus 3, x minus 2. And super clear, we can cancel out. Why not? The factor is common in the top and the bottom. Now, this is equal 1 in the top, x minus 2. Do I need to interpretation this? Interpretation, and also state the domain, que is the last part, no? Interpretation. Okay. If you, okay, entonces, okay, the interpretation is, bueno, okay, professor, this expression is equivalent 100% of this, or no? The answer is no. The answer is no. So this is equivalent. This is equivalent. Equivalent. This symbol indicates equivalent. It's the same to this. You consider and x is not 3. Now this statement, que es a compound statement because I connecting by and, is equivalent to this. Entonces es obvio que the domain of this expression is all real number. Let me try again to do here. It's all real number except 2 and 3. It's exactly the same sketch of this. I did intentionally. Okay, it's all real number. Not necessary to do again. Okay, this the domain is open the curly bracket, x such that, no 2, and no the comma. This comma is equivalent to say and. So this and this. And this. Okay, in the interval notation, you know, I don't need to repeat again as this idea. But I want to stop a little bit to understand what is the difference between 2 and 3. Because both, so as you evaluate P and 2, is undefined, it's obvious, right? Undefined, look at that. 2 minus 2, well, you evaluate here is the same, no? It's 2 minus 2 is 0, at least 1 0, I don't care. This, but P and 3 is also undefined. Undefined. Because it's 3 in the denominator, right? It's 3 undefined. But 3 and 2 both are restriction. But 3 have another connotation different to the 2. Because in 3, at x equal 3, we have the famous whole. Whole is something similar to this. So when you are doing the graph, I promise, I bring example after that, similar to this. When you are doing the graph of this function, the p function, and p function, I have no idea. I have no idea. But I know that in 3, this is 3, this is 2. In 3, we have a whole, like that. This is 2D. Suppose that we have x-axis and y-axis, no? We have a whole. I suppose I have no idea the rest. You write like that. It's a whole. It's a whole. A whole. However, in 2, no whole. In 2, we have another thing. It's called asymptote. Asymptote, we discussing in detail after that, I promise. Asymptote is one vertical asymptote. Vertical asymptote. It's a vertical line. Get the curve, in this case, the curve approach it, but never touch. And increasing forever to infinity. Maybe like that, or maybe in another direction, or maybe in different direction. This is the asymptote. So this is the differences that you need to understand between the nature of two, que son defined, but in two we have asymptote. How do you know? Well, asymptote. Because when you eliminate, so the factor gets canceled out, it's a whole, always, always. This is the asymptote, however, in three we have a whole. So when you are doing, for example, the graphic of this function, is exactly the same of the graph of this function, except in three. Okay, in three, the original have a hole, in three, and the next after the simplification, when you eliminate the hole, we have no hole in two. So we can use in our imagination. So you have a complicated expression, you factor it, you cancel out the common factor if exists, because not always exists. It exists, you cancel out, and you know that the factor gets gone. It's a whole. You focus it, and the new expression gets easier than the original, and you are doing the graph of this with a whole, but you include the whole that the original function has. Okay? Confusing a little bit, I understand. And this is just the beginning. I introduced artificially the new idea for the vertical asymptote. Okay, I want to discuss it right now in few seconds. So we discussing now the idea for the vertical asymptote. This situation never happened in polynomial function. Remember, polynomial function is smooth, continuous. Rational, no. Rational is discontinuous. Maybe it's smooth, pero this, bueno, it is continuous. Si es discontinuous, no smooth. Okay, let me see the vertical asymptote definition. Definition. Okay. I introduce one, well, let me try to see geometrically the idea. And after I complicate with the notation and definition. Suppose we have four possibilities. It's a four rectangular coordinate system, XY. Suppose add one value, suppose add x equal 2, for example. I don't know. I select 2 because I want 1, 2. Here we have asymptote. 1, 2, we have asymptote. 1, 2, we have asymptote. 1, 2, we have asymptote. This value is 2, 2, and 2. By the way, the equation for this line is x equal 2 because it's a vertical line, no? Vertical asymptote is vertical line. And normally, when we are doing the graph, we represent using dotted line. Because asymptote is auxiliary contraction can help me to understand the curve. But actually the curve is a curve que no include the asymptote. The asymptote is auxiliary contraction can help me to understand. That is the reason that we put in dotted line always. Okay, then we have several possibilities. Like that, like that, like that. No, sorry. Like that, and like that. And how do you know? Well, it's easy. So basically, the definition is when the x approaches to 2, okay, this symbol, I want to explain what means that symbol. Approaching means one value close to 2, so like x is close to 2. Okay, approach, not necessarily 2. 1.9 or 2.1, okay, or 2.0001. approach. But we have two possibilities to approach it. The X approach it to 2 plus. Wow, what mean 2 plus? No, it's not positive 2, it's 2 plus. It's X close to 2, pero X is greater than 2. Okay, as you approach it, so we have two directions to approach it to 2. We can approach it to the right, or we can approach it to the left. To the left. So when it's 2 plus, it's to the right. This is equivalent to say, that you evaluate in 2.1 or 2.0001. However, when your X approach it to 2 minus, it's not negative 2. This minus is, so you need to understand the difference between minus 2 and minus. This sign indicates direction. This sign indicates the sign of the number, right? But in this case, everything is positive 2, no negative 2, positive 2. And 2 minus indicate that you are X is close to 2, to 2, pero X is less than 2. So you approach it to 2, pero to the left is maybe 1.99999. In this case, 2.001. So you pick, not necessarily too close. You pick one arbitrary value after the 2, and you evaluate. Oh, it's positive. And you take one value before 2, and you, oh, it's negative. So I know that the behavior look like the first type 1. So you evaluate after, before, and both are positive. So this is type 2. And so you evaluate before and after, and this is positive and this is negative, entonces es type 3. And also, see both are negative, it's type 4. That's easy. No big deal. That you discover the potential, no. The value that exists the vertical asymptote. Okay, entonces, what is the formula to determine the value of the vertical asymptote? Well, you take, remember the rational function. Rational function is f of x equal p of x divided by q of x. You factorization, this and this. And after the factorization, I assume the common factor is canceled out. O sea, no common factor. No common factor, because I delete. No common factor. Now you take the expression in the denominator, que q, forget about the top, and you enforce it to be 0. And you apply your algebra and solve for x. And this is my potential. Potential, no. This is my vertical asymptote. What is the next step? Well, the next step is evaluate. Suppose that the solution is 2, 3, 4 of this equation. And you evaluate a little bit before 2 and a little bit after 2. You select 1.9, 2.1. Evaluate 2.9, suppose, I don't know, 3.1, 3.9, 4.1. And only to determine si it's this kind of asymptote or another kind. Okay? So now, what is the formula for finding? You have to remember, because this topic have a lot of information. Now, to say, I don't remember, professor, what is the formula? This is the formula. Take the polynomial in the bottom, equal to 0, and determine the 0. How you determine the 0? One of use factorization, use synthetic division, the way you know when we study in detail the factorization. Okay, no more blah, 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 blah. Too much blah, blah, blah. Let's go to the first example. Do you have some question or no? Let's focus on the example 1. Maybe in example 1, you clarify very well everything. Example 1. The function is f of x is equal 2 over x minus 3. Okay, it's a rational function. In the top, we have polynomial degree 0. And the bottom, we have polynomial, but it's a polynomial, no, it's a binomial, no, but okay, but degree 1, linear. We can factorization? No, we cannot factorization. The factory form is a perfect coincidence with the original. There are no difference. Okay. So what is the idea to find the vertical asymptote? Vertical asymptote. Well, you take the polynomial at the bottom, you enforce it to be 0, and you solve for x. X equal 3. Because I know that at x equal 3, we have a famous vertical asymptote. Okay. Now, that's it. No. I need to verification before and after. For example, I select, okay, this is my x-axis. I know again 3. We have vertical asymptote. Yeah, I select. But no, I don't want to complicate my life. When you have only one, not necessary to take 3.1, 2.99. You take 4, and you take 2, a little bit, and you evaluate the original function in 2, and you evaluate the original function in 4. And 2 is easy. Look, and 2 is 2 over 2 minus 3 is 2 over negative 1 and negative 2. This is negative. Negative 2 here. And 4 is 2 over 4 minus 3 is 2 over 1 is 2 over positive. So I have a roughly idea how look like my function. I don't know exactly the rest, but I know that we have a vertical asymptote at 3, and the behavior is like that. Because remember, we have 4 kinds of behavior. We have this kind, this kind, this kind, or this kind. And you need to do them. In this case, is this behavior. Okay, guys, just in case I don't like that, I go to Desmos. Let me share the screen. Desmos. Okay. And just in case I want to do the graph in Desmos. I prepare here a different example. Example number 1. Look at that. Ooh, nice. Recommendation. You copy the function. You copy the points. You evaluate 4 and 2. You can use it here. Remember, Desmos is graphic calculator and also is regular calculator. We can compute it. So you define, you define f of x. You can evaluate 4 and you can evaluate 2. But this is elementary, right? And you type in here the point. And don't forget, look, very important, the vertical asymptote. Okay, always we using black color and dotted line. I select dotted line, not solid, dotted line. This is a convention in our subject. Any asymptote, vertical, we study another asymptote in your moment, no? The convention is black color, dotted line. Entonces you know how in the test, for example, you click here, we want to share the graph, okay, and you create the image and export the image, and you send me back, okay? Download and send me back. Okay, any problem, we can use always Desmos. Always Desmos. Any question? Confusing, very confusing, no question, super. Jasmine. Okay, Jasmine. Okay, let me try. Let me go again to whiteboard. Whiteboard. Okay, do you see whiteboard now? Let's move on to example 2. Example 2 bring me new situation. Example 2 bring me new situation. Example 2. Okay, the function now is called G. And the function is x minus 3, exactly we did before. Is x squared minus 5x plus 6. Okay. Entonces, what is the goal? What is the goal? Well, the goal is do the graph, no? Always do the graph. Now, what should I do? The step number 0, the first thing you should do in analysis of the rational function is express it in factory form. Express it in factory form. It is x minus 3, but this is x minus 3 and x minus 2. And immediately you cancel out the 3. Yeah, I know that at x equal 3, we have a whole. We have a whole. Now, my equivalent in between quotation mark is 1 over x minus 2. I know very well that these and these are not 100% equivalent. Because, and the whole no, because I eliminate the whole. But I focus in the, so I copy, let me copy another name, G1 of X. Because they are a family, no? Entonces 1 over X minus 2. So I know, I do the graph of this, que is easier than the graph of this, but the only difference is a whole entry at 3. Okay. So I investigate, wow, one more time we have a vertical asymptote. How you find the vertical asymptote? You take the polynomial after the simplification in the bottom, and you enforce it to be 0 and x equal 2. So at x equal 2, we have a vertical asymptote. At x equal 2, we have vertical asymptote. Okay. Okay. So now I have no idea how the behavior. So I evaluate a little bit after I evaluate. Suppose this is my line. I know that 2 and 3 we have a whole, remember. In 3 we have a whole, but in 2 we have asked. Something like that. Entonces you evaluate before and after. Here, I evaluate. In 3 we cannot evaluate because have no. Well, you can, but no. Because I know that G and 3 is undefined. G1 and 3 no. Pero bueno, okay, you can evaluate, yeah. And 1 you can evaluate. For example, you evaluate in 1 first. You evaluate G1 and 1. Not necessarily evaluate in 3. Because 3 is more complicated expression and 1 is easier. So 1 over x minus 2, evaluate at 1, x equal 1. Es obvio que 1 over 1 minus 2 es 1, ese es negative 1, es negative 1, ¿no? Entonces es negative. Negative, sorry, negative. Negative. Okay, negative. And you can evaluate 3, you can. But I don't like 3 because 3 I know is undefined, but undefined the original, but not undefined the another function que es equivalent. Let's do in y, no. G1 and 3 is 1 over 3 minus 2, que es 1, entonces positive 1, es positive 1. Pero I know, si I want to do the graph of the origin, I know que we have a hole here. So the behavior, I suppose, can look like that. I don't know exactly what happened in that part. That part we don't study. But I know very well in that part, we approach it to and never touch. Approach. The distance between the curve and the asymptote is smaller. Decreasing. However, never touch. Never illegal touch. And the other direction, something like that. Okay, super. Any question? In both cases, in both cases, the original G evaluating 3 is undefined. The original G evaluating 2 is also undefined. Okay, let's see what's going on. Let's see how you can see in Desmos. Let me switch into Desmos. Look. Okay. Do you see Desmos now or no? Example 2. Good. Example 2, Yasmin, thank you. Example 2. Remember, this is the expression. I copied the original expression, no? We discover that we have, look at that, we have the vertical asymptote at x equal 2, like that. And in 3, we have a hole. Actually, I put 3,1. But remember, this one is the value for G1, que es the equivalent. Pero I know que es 3, undefined in the original, no? Suppose curiosity, just curiosity. Suppose I want to do here the graph of the G1. Suppose G1 of X, just curiosity, equal, after the simplification, after X minus 3 is cancelled, in the top we have just 1, division by, let me using the keyboard, I feel more comfortable with the keyboard, X minus 2, no? X minus 2, X minus 2, X minus 2. Wow, do you see now in red color the graph of the after the simplification? It's exactly the same. So they are perfect coincidence between the blue graph and the red one, except in the hole. Okay, so now you see clear that they are equivalent, but no 100%, because on the hole, que is the value that you eliminate, we have a hole, and the other function have no hole. I don't know if it's clear or no, guys. It's clear or it's confusing? Clear or confusing? Clear. Okay, Yasmin, clear. Okay. Okay, thank you. Okay, let me see if we come back to the whiteboard now. Whiteboard. Okay, there you go, whiteboard. Okay, let me erase everything. Okay, so we 3 different type of this problem. Yeah. No. Okay, you cannot control me. I know very well what is my way to teaching that. Basically, listen to me. You talk to me, I am professional. Okay, look, the thing we are doing now is discussing theoretical part. When you complete the picture, you see big picture and the theoretical part. I have a special, for example, for you. Okay? So now, stop for a moment. The only thing you studied so far is the domain and the vertical asymptote. That's it. And I did 2 elementary kindergarten example of this. Let's move on to the horizontal asymptote. Wow, professor, how many asymptotes we need to study? Why don't we study 3? This is the second definition. Okay, horizontal. Now horizontal. Because I suppose we understand a little bit, not 100%, but we understand a little bit vertical. Now I want to introduce horizontal definition. What is the idea for the definition? This is very, very similar to the end behavior. Okay, we studied in the polynomial. But in this case, it's a little bit different and interesting. When you talk about end behavior, that means x approaches to infinity, positive or negative, in both directions. By the way, specifically in rational function, the end behavior in positive infinity and negative infinity is a coincidence. Not always happen in all the functions. All the functions we study in the next chapter, like exponential function, have not that property. But the thing is, in the rational function is the same value. So this is one value of the y that I want to call d. So in other words, when the, okay, let me see. This is the Oriental line, infinity positive, infinity negative. I don't know exactly what happened here in the curve, but I know that when the x approaches to infinity positive and infinity negative, the curve approaches to, let me use in green color, to the one line, okay, by the way, is a horizontal line, okay, and the equation of this horizontal line is y equals d, this quantity. I suppose that the curve, hypothetically, I promise that we see example, suppose that the curve approaches to this, for example, in that direction. There are many possibilities. One possibility is like that, suppose. Look. Another possibility is that we have in the middle, vertical. Another possibility, let me use another color, is that the graph look like that. Cross the horizontal and after approach it but never touch. Okay, this is the most common case is the blue case. Well, maybe like that or maybe like that. But it's important que, oh, what the hell? Okay, look, when I approach it to infinity, the curve try to reach the y value d, no? In both directions. And it's impossible in rational function have that situation. Look, impossible. We have one asymptote here, another horizontal asymptote here, and the curve is something like that, and something like that. No, this situation never happened in rational. In rational, never. We have the same value in positive infinity and negative infinity. Okay, another function, yes, of course, pero this no. Entonces, bueno, okay, professor, blah, blah, blah. Too much, blah, 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 but I don't understand anything. Well, let me explain the rule to determine the horizontal aspect. You see the example, you understand very well. Well, identify. How you identify? Identifying horizontal aspect. How do you know that we have? What is the glue to give me information? Well, the glue is if suppose P of x divided by q always is a classical, general form to express the ratio. If the degree of the polynomial b, que is the top part, is equal, same degree, the degree of the polynomial q, same degree, so in other words, in other easy word, when the degree is the same, the conclusion is then we have horizontal asymptote. Pero at what value is the problem? At what value? What value? Okay, let me explain using example. Okay, the clue of the identification that we have or no horizontal asymptote is the degree. Suppose this example, example number 3, no? That's 3. Suppose the function g is equal 7x squared plus 2x. Okay, in the top we have polynomial degree 2, and the bottom we have polynomial degree 2 also. Okay, it's binomial, but it's binomial degree 2, binomial degree 2. Now the first thing you should do is analyze. What is the degree? What is the degree of the polynomial in the top? 2. This is higher exponent, no? What is the degree of the polynomial in the bottom? Also 2. Okay, that satisfies perfectly this idea. Same degree. The rest of the problem is what value? What value? Look, you try to understand the new idea que es the dominant. Dominant. What is the dominant term? Well, the dominant term, okay, this one roughly approximation dominant. Remember, I copy again my original problem. Where the supposition is x is a huge number, positive or negative, million, trillion. I know que the exponent, the greater exponent increasing faster. So everything increasing. This is increasing, but this increasing faster than this because degree 2 is a parabola, no? And degree 3, suppose we have another problem. Now you take the higher degree. Now this is approximately, and the end behavior stay alive only 7x squared. And it's completely negligible. And this is completely negligible. And the bottom we have 4x squared. And we can simplification. And the answer is 7 over 4. And this is the formula or the expression in this specific example of the horizontal asymptote. So we have horizontal. Yes, we have, because the degree is the same. At what value? You take the dominant term. Dominant is the greatest point, no? In the top, in the bottom. In this case, they are perfect coincidences because they're the same degree, no? So you ignore totally the rest because we are talking about end behavior, okay? And this is the way to find the horizontals. Okay, this is just the beginning, guy. I promise I want to complicate more this because I want to complete it, this idea. This is just the beginning, but it's clear, right? It's clear. To prove me that you understand, I bring 2 examples, and you help me. Example 4 and 5. And 5. You help me to understand. No, question number 1. The is yes or no question, no? We have or no, yes or no. And the second question is at what value? Okay, suppose the function h of x equal 8x squared plus 9x minus 5 divided by 2x squared plus 1. And the second function p of x is equal x squared plus 7 over 11 minus x squared. Okay, and the first one here. We have or no? Yes, no. Answer me, please. Yes. Jasmine say yes. She's right. Everyone understand? Because the analysis of the degree, degree of the polynomial on the top is 2. Degree of the polynomial at the bottom is 2. So the answer is yes. We have horizontal asymptote. At what value? is my second problem. At what value? We apply the idea for the dominant. What is the expression dominant in the top? A. Aha! Okay, she say is slick soccer 12. Wow. What is your real name, Mr. or Miss? Sean. What's say Sean? Sean. Sean, no? Sean. Sean. Mr. Sean say get 4. It's obvious. It's obvious get 4. Because the dominant guy is in the top is 8x squared, and the dominant in the bottom is 2x squared. And use simplification, the answer is 4. That's the y equal 4 represent our horizontal asset that we discovered exists first, and second at what value for. Who helped me in the example 5? In the example 5, yes or no? Yes or no? Yes or no? Yes or no? Yes, of course. Okay, Sean. Sean say yes. At what value, Sean? Or another participation, come on. Yes, Addis Betancourt say yes. Because degree is 2. Look at that. Degree, polynomial, degree 2. Is negative 1. Very well. Degree 2. Degree 2. Now, it's obvious that the dominant expression in the top is x squared, and the dominant expression, I put intentionally to confuse you, but no Sean. Sean understand very well. Can you delete mentally 11, because 11 is a constant, degree 0, and the answer is negative 1. Entonces, y equal negative 1 is our horizontal. Everyone understand? Okay. Number 1 is, si you want to investigate the domain, no, coño. Horizontal asymptote, you analyze degree of the top, degree in the bottom. Si it's the same, we have. Definitely, we have. But is the only possibility? No. Unfortunately, no. Unfortunately, we have another possibility that we have. Yes, when the degree in the bottom is greater than degree of the top. I call this like a special case. We have a special case. Special case in which degree of Q is bigger than degree of P. In this case, yes, we have. Yes, we have. But it's special. Let me see why it's special. Yes, we have. It's always at y equal to 0. Okay, and that's it. No more case. So we have the regular case when the degree is the same, and we have the special case when the degree at the bottom is bigger than the degree at the top. Let me see one example. Example number, what number is this? Number 6, no? Let me see, number 6, yeah. Number 6. Example number 6 is the function h of x equal 5 over 4x squared plus 9. Wow, what the hell is that? Confusing. Well, degree of this is 0 because it's a constant, no x. Exponent 0. You suppose it's x to the 0, no? Invisible, of course, okay, 1. And degree of this is 2. Satisfy perfectly the condition for the special case. Yes, we have. What is the reason? The reason is, look. Si you analyze dominant. Dominant at the top is 5. Well, we have only 5. See, I delete it to say nothing. No. It's the only guy. But at the bottom, I can remove this. Okay, I can remove and delete, ignore this 9. The dominant increasing faster than this. Because any expression like a reciprocal function or reciprocal function square or reciprocal function cubic, it's obvious that when the x approaches to infinity, y approaches to 0. Okay, because you know this stays the same, constant, but this increasing and decreasing. So one number, 100, 1 million, it doesn't matter, divided by x, and x I suppose que es increasing forever, infinity positive or infinity negative, es obvio que es 0. Do you understand this or no? Because I can show you, no? Or no? Numerically, mathematically, arithmetic part, right? Do you understand the arithmetic part? The denominator increasing, the entire rational or fraction decreasing, no? It's going down. It's going down. That is the reason, but no negative, never negative. Okay, for example, see, we can see, for example, the classical f of x equal 1 over x, the reciprocal function. The reciprocal function degree is 0 and degree is 1. Entonces we have horizontal asymptote at y equals 0. So we are doing something like that. Look here. This is my horizontal asymptote. By the way, we have a vertical asymptote because you take the expression at the bottom and force it to be 0, and this is my vertical asymptote. We have vertical asymptote here at 0. Everything is 0. This is vertical asymptote. Yeah, I know that my graph, when I plot different points, additional point, look like that. Okay, we have vertical asymptote and we have horizontal asymptote. More clear, entonces basically, the thing that the student don't remember very well is that we have two cases and we have horizontal asymptote. The regular, when the degree is the same, and the special, when the degree of the bottom polynomial, denominator polynomial is greater than degree of the top. Okay, I bring another example to illustrate everything about the horizontal asymptote. And we have one more problem, one more situation. Well, okay, professor, it's easy to understand when it exists or do not exist. It's easy somehow determine at what value is the horizontal. But one new thing that I want to discuss now is determining ing where a graph crosses a horizontal asymptote. Oh, it's a new situation. Huh? This is very important. Okay. Let me try to introduce this idea. Okay. Look, the vertical asymptote for sure. The curve never touch. However, the horizontal maybe yes, maybe no. It's very seldom can happen, pero happen. Okay, suppose another example here. This is the horizontal asymptote. Then our graph, suppose que es black color, maybe look like that. Approach now, but never touch. 2x approach to infinity point. However, this is important point. Determine the point where the graph crosses the horizontal. Entonces, I want to explain how we discover that point, que es important. Important point. And maybe exist or maybe do not exist. and only is only one. Si exists is only one, not two. Okay. Okay, so I bring another example. I don't remember what number is this example. I suppose example 8, no? I want to investigate in detail that function. 8x squared plus 9x minus 5 divided by 2x squared plus 1. Entonces, we focus only in the horizontal aspect, guys. I don't care vertical aspect, no. In the real life, the example that we study, I suppose que next class, we study 3 or 4 examples. We study everything at the beginning. Yeah, I want to explain the guideline, no? To face this function. Okay. Question number 1. Horizontal aspect exists, yes or no? Exist, yes or no? Yes. Okay. The idea is clear. The degree of the polynomial and the top is 2. Degree of the polynomial is 2. Same degree we have, yes. And this is not special. No, it's regular. Randy say a 2. Y equal to, where come from these 2? Well, these 2 is, you apply the dominant idea. This dominant expression in the top is 8. The dominant expression at the bottom is 2x squared. So you take the higher exponent always. When you simplification, this is canceled, and this is 4. Y equals 4 is the horizontal. The new situation that we study now in this example is if when we are doing the graph of this rational function, this function crossed or no these horizontals, touch or no. This is the challenge now. Discover this and what value, by the way. Well, this is relatively easy because you enforce it. One equation like that. You copy the rational original function and you enforce it to be 4, equal to 4. That this equal to this. Maybe if this is impossible, see, never cross, this equation have no solution. But see, this equation have solution, obviously, yes, touch. Okay? This is classical in algebra. When you want to intersect in two things, you enforce it. This is equal to that. You manipulate algebra. And we discover, no. It's a contradiction. Contradiction, how you discover contradiction? When you get 2 equal 4. It's a totally false statement. It's a contradiction, so therefore never cross. So you get one value to satisfy this, you get X value to satisfy this. Okay, I propose you for solving this equation, cross multiplication. You multiply 2x squared plus 1 times 4. Gives 4 times 2x squared plus 1. And you multiply this times 1. And 1 is invisible multiplier, entonces es exactly 8x squared plus 9x minus 5. Okay, now you remove the parentheses, apply distributive property. 8x squared plus 4 equal 8x squared plus 9x minus 5. Bueno, es obvio que this cancel, yes or no? Now I solve for x. Entonces 4, stay, I move 5 to the other side. It's equal to 9x. 4 plus 5 is 9. Divided by 9, both sides. Wow, we discovered that x equal 1 is the famous point in which our original function crossed the horizontal asymptote. Okay? However, I want to express it like an ordered pair, x comma y. Yeah, I discovered that x is 1. And what is the y value, guys? Help me. Help me. What should I do for finding the y value of the famous point? What is the y value? Plug it in? Or no? Or directly, I can infer. Hey, are you there? 4. Es obvio que 4, Sean. Because the value y que intersecting 4, 1,4 is the famous point in which our original rational function crossed, in this example, the horizontal asymptote is at y equal 4. I promise that we see another example that when you set up this equation, we found no solution. And when you found no solution, contradiction is because this famous point I want to find do not exist. Let me show you in Desmos. Let me show you in Desmos now. Okay, example 3, no? Example 3. Okay, I want to switch into Desmos. Switch into Desmos. Okay, Desmos now. Okay, there you go. Cool. Do you see Desmos, right? Okay. Let me see if this example 3 or not. Oh yes, look at that. This is the example 3. Look at that. This is my function. I type in here ax squared plus 9x minus 5 at the top divided by 2x squared plus 1 the bottom. And the famous horizontal asymptote is at y equal 4, and the super famous point when it crosses is 1,4. It is. End the story. And you see, wow. Look at that. Look at the aim behavior. Suppose positive infinity. Let me make it zoom. Do you see the curve approach but never touch? Never touch. Only touch in one. Because in one cross it. And the other direction in negative infinity happen exactly the same. Approach but never touch. Any question? Any question? No? However, I have a question. Professor, and this function have no vertical asymptote? I don't see here vertical line, dotted line. No, I don't see. The reason is no. And let me explain why no. Okay, I come back to the whiteboard to explain the idea. Okay, whiteboard, you see whiteboard? Okay, I try to understand why we don't have. Yeah, thank you. I try to understand we don't have vertical asymptote. Well, what is the formula? One of the formula is, maybe we are doing the factorization. No, but in this case, it's crazy. Then, look. You take the polynomial at the bottom, que is 2x squared plus 1, and you enforce it to be 0. This is the formula. The formula to find the vertical asymptote is after the factorization and simplification. The thing, okay, we take the polynomial at the bottom and force it to be 0 and solve for this. When I solve for this, it's -1 divided by 2, x squared is equal to -1/2, square root both sides. It's imaginary, right? H1, you don't need to finish because immediately you realize que it's imaginary. Remember, when you try to find something in algebra, I want to find something, but in middle of the process I discovered que es complex or imaginary is because do not exist in the real field. O sea, do not exist. That is a reason that we have no vertical asymptote. We have only one horizontal asymptote at y equals 4. And by the way, we discovered one famous point, que is the point 1,4, in which the curve crosses the horizontal. Any question? Any question? Any question? Any question? No. Okay, Yasmin. No question. Okay, so now I want to discuss it with you the last kind of the asymptote that we have. The last kind, que es slant or oblique asymptote. So far, we study vertical, like that. Vertical asymptote. And the equation for the vertical asymptote x equal one number, no? X equal 2, suppose 3 or 4 or negative 2. We have horizontal. Que es y equal a number. Horizontal line, no? Slope 0. And slant asymptote is a typical line like that. Maybe a slope positive, y equal mx plus b. Okay, this is a line. Now we need to discover a slant asymptote. Okay, entonces when you identify que we have a slant, you identify que we have a slant if the degree of P, if the degree of P, remember P is in my supposition, the polynomial at the top, is greater than the degree of Q, pero if the degree of P is greater than 1, is greater than, but let me write in English, is greater than, no H, greater than plus 1 than the degree of Q. Let me translate in easy word. This is another example, example 7, no? Suppose f of x equal x squared plus 1 divided by x minus 1. Suppose que you face that problem. Okay. Degree of the polynomial at the top. Esto. Degree of the polynomial at the bottom. Es 1. Satisfy perfect this idea. Degree of the polynomial in the top, que P is greater than 1. This is degree 1 plus 1 is 2. Si es, suppose que es 3 and 1, no, should be greater than, should be, no, must be, mandatory, greater than 1, plus 1. Suppose que 3 and 2, yes. Satisfy perfect this idea. Okay? And obviously, we have no horizontal asymptote. This idea is completely mutually exclusive. Si we have horizontal, we have no slant. Slant asymptote, no. Si we have slant, we have no horizontal. Pero both is impossible. Both is impossible in any problem. Okay? And how you find that? Well, easy. easy. You are doing long division or synthetic division. Either way, in my opinion, much better long division because in this case, it's possible doing that in both ways because the degree of the denominator polynomial is 1. But when the degree is not exactly 1, to say long division is only possible. Because remember, synthetic division is shortcut of the long division when the degree of denominator is 1. Okay, so let's do in long division. You copy inside the box the polynomial on the top. Don't forget x squared plus 0x plus 1. Don't forget to complete it. See one element is missing inside the polynomial degree 2, degree 1, degree 0. No? And outside the box, x minus 1. And we start. It's obvious que es x times x is x squared, and x times -1 is negative x. Entonces negative x. Here I put in the same column of this, no? By subtracting, change the sign. This is the disadvantage of the long division. Okay, you have to remember that you multiply and subtracting. This is cancel, and this is just x plus 1. Bring down 1. Finally, plus 1, because 1 times x is x, and 1 times 1 is negative 1. By subtracting, change the sign. The answer is 2. The remainder is 2. Okay, so what are the answers? What are the famous answers? Well, we prove mathematically it is expression que es x squared plus 1 divided by x minus 1 is equivalent, it's the same, using algebra. X plus 1 is a quotient. X plus 1 plus or minus, I don't know, in this case plus, because the remainder is 2 divided by divisor. This and this is equivalent. This is the same thing of this, equivalent 100%. It's the same, equivalent. But in this case, you see clear that that part represents the slang asymptote. Okay, the slang asymptote, remember, y equal mx plus b. In our specific example is y equal x plus 1. But b is 1 and slope is 1. Okay? And we can do the graph of this slope, this slang asymptote, sorry. Okay. The graph is easy because it's y in a set 1. And the slope is 1. So this is 1, 1, 1 here. That it's a wrong rise. And we're connecting this. This is my slang. Past. Okay, and this is one part of our problem, no? We have horizontal. No, horizontal, no. Because if we have a slang, we have no horizontal. In another direction, if we discover that we have horizontal, we definitely have no slang. No, it's a contradiction. They are completely different idea. However, vertical we have, vertical, yes. Vertical we have. Remember, what is the idea for the vertical? The vertical is you take the polynomial and the bottom cube. The formula for finding vertical asymptote is this after the simplification, and that way we can know simplification. You take the polynomial in the bottom, gets x minus 1, you enforce it to be 0, and x equal 1, we have a vertical asymptote. So we have here in 1, this is x-axis, this is y-axis. And 1, we have another asymptote, okay, vertical. Now that probably contains slang and vertical. Guys, the rest is, for example, select totally arbitrary. No arbitrary. I explain the rule in your moment. No, now my idea now is explain slang asymptote. This is what's complementary. And the other thing I try to explain now, you plot different points, it's totally complementary. In your movement, I promise I explain how you select this point. Okay, how many points you need, minimum, no? Okay, this is the idea. Okay. Entonces, si I summarize a few words, the thing que I want I studied today was we have asymptote. We have three kinds of asymptote: vertical asymptote, horizontal asymptote, and slant asymptote. Vertical, the formula is this. Horizontal is the degree analysis. You analyze the degree on the top. We have two possibilities. The same degree is a regular, and when the degree at the bottom is bigger, not necessarily by one, bigger, is a special case. And then you are doing long division, and you take the quotient part, represent the slant. Okay, so this is a moment. I want to explain something important. In my opinion, is the most important in our lecture today. And now we stop because next class we are doing this a problem. No, I don't know if we have time or not. Okay, this is the guideline that we following always to graphic a rational function. Okay. Step one. Step one. Step zero. Step one is the first one. Okay, they are polynomial with no common factor. Okay, in other words, no common factor. I factorization the top bar, suppose x minus 2, x minus 3, over x minus 2, x minus 4, x minus 5. Suppose this. And you eliminate the common factor. Yeah, I know that at x equal to, we have whole. Okay, it's the first thing. The first thing in the step one is factorization, the top part, factorization, the bottom part, eliminate the common factors, gone, and I suppose they are a whole. And we pay our attention in the rest. And number one, I suppose that we have polynomial with no common factor. Okay? Don't forget that, guy. Number two step is find, super important point. Find y-intercept. A super important point. And what is the formula to remember y-intercept? Well, using function notation, evaluating zero. End the story. It's a formula to find y-intercept. Okay? And the third step is find the x-intercept. Well, what is the formula for find the x-intercept? F of x equal to 0. This is a little bit more complicated because to find, or for finding the x-intercept, you set out the equation. Let me explain a little this part. Normally, our function is rational. Entonces, es a division, P divided by Q. Okay, my f of x and the rational specifically have that format. Equal to 0 means que it's equivalent to say that the polynomial on the top is equal to 0. Yeah, I don't care the polynomial on the bottom. This is totally irrelevant in this analysis. You focus it in the 0 of the polynomial on the top, and that's it. And that's it. Okay. What is the fourth step? Well, the fourth step is determine. Xiomara. Okay. So another student, annoy me, gets another class. Okay, I'm teaching now. Okay, number 4 is determine the vertical acid. Vertical acid. Remember the formula. The formula for finding the vertical acid is super easy. It's you take Q polynomial, okay, in this case I ignore, look, but you take now and you force it to be 0. And recommendation, doing, then, this is an important moment for me. We are doing a dashed line or dotted line like that. Okay, the solution for this equation. Okay. Number 5 is determine the horizontal asymptote or, because of mutual excluded, you have horizontal or slant asymptote. And also, why not? Using dashed line. Remember, the analysis, this is clear, is degree analysis. Degree analysis. See, the degree is the same, horizontal. The degree of the bottom part is bigger than the degree of the top, it's a special horizontal. If the degree in the top is greater than 1 degree of the bottom, it's a slant. Greater than 1, si es 2, no. Okay, it's a slant. Okay, number 6, que is important in my opinion, and the student forgot always, is test of symmetry. Let me explain what is important is. Test of symmetry is easy. You spend only 2 seconds to do that, but it's usable because, okay, you are doing reflection like that. When you are doing the reflection of the original function, it's exactly the same of the original, because it's even. Entonces, si es even, I take advantage this fact, and I know that my function is symmetric with respect the y-axis. In other words, my function look like that. Okay, the negative part is exactly the same of the positive part. So if you find, for example, for 2, one value, I suppose that we have in -2 the same value. In other words, you need to do only the positive part because the negative part is the same, and you save time. See. Okay, it's super easy. Replace x for negative x, and you manipulate some elementary algebra, and you get exactly the same function. Doesn't change the function. It's because it's even. The positive part and the negative part is the symmetric. It's the same. Because I care only the positive part, because the negative part I know gets the same value of the y. However, sometimes happen when you are doing that reflection, we have minus sign, not exactly the same, opposite sign. So this is odd function. Okay, this situation happened, but I take advantage also this, because suppose that this is like that, and this is like that. Okay, so you take, for example, number 2 point, and you get one specific value, in this case positive, and -2, we have exactly the same, but the actual value. So this distance and this distance the same, but opposite sign. Opposite. This is symmetry. Symmetry with respect the y-axis, and this is symmetry with respect the origin. Otherwise, no symmetry. See, the test of symmetry failed. Okay, unfortunately, you need to take the graphic of the positive part completely different to the negative part. Okay, but you spend 2 seconds and you save time. 2 seconds. Only 2 seconds. Okay, now. The last step, in my opinion, is very, very important. Important that you understand and master that. Okay, this is the number 7, que es plot additional points. And the classical question is, Professor, how many points addition I need to plot? Well, okay. I want to answer that question. Okay. In that moment, you have, for example, the x-axis. This is my famous x-axis. I discover the vertical asymptote, suppose 2 vertical asymptote. Vertical asymptote number 1, vertical asymptote number 2. And also we discover the x-intercept point. Suppose that we have 1 point here, 1 point here, and 1 point here. This is, remember, this was, okay, where come from this guy? This guy was the solution of this equation. Where come from this guy? This guy was the solution for this equation. This guy. Okay, this, and this, no? How many points? How many additional points you have to take? Addition. Well, and this specific problem, no, it's not too complicated. You take one here, arbitrary, totally. You randomly select. After this intersecting point, you select in between the intersecting point and the vertical another point. You select between the vertical and the other intersecting another point. You select here another point. You select another point, and you select another point. 1, 2, 3, 4, 5, 6 points. In this case, not only 6, depending on how many vertical asymptotes you have, how many intersects you have, but at least this is the minimum requirement to select the additional point. And it's easy, you select totally arbitrary inside the interval and plugging it into the original using the calculator and get the story. Clear? Okay, so say I want, because we have time and you are excellent students. Wow. Present one first problem. Present one first problem, and you guide me. What should I do step by step? No. Suppose this function. Okay, let me call problem. No example. Problem 1. I promise in next class we are doing problem 2, 3, 4, 5. Okay, until you get the idea. Suppose f of x is equal 4x divided by x squared minus 4. This is my function, it's given. Okay. I want to start. I'm following strictly the guideline. Number 1 step, number 2 step, number 3 step, number 4 step, number 5. Until, what is the next? Well, last one, 7, no? 7. Okay, what is the first step? What is the first step? Step 1. I copy here. Step 1. Guide me. Please, help me. Nobody can help me. I know you don't know. You need to read. What is the first step? Degree 1. Okay, but no. This is not the first step. Degree 1. I agree with you. And degree, this is analysis of the degree. No. This is the, no. Oh, factorization. Very, very well. Very, very well. Okay, this is my function, and factory form is 4x. It's a monomial, stays the same, but this is different of x squared. And the factorization is xx to 2 plus or minus. Yeah. The factor form. And my question is, we can cancel out some factor or no? Yes or no? We can cancel out some factor or no? Yes, which one, Randy? What factor we can cancel out? What factor we can cancel out? Activate the microphone if you want to explain me. What factor do you cancel out? No factor. No factor. In the top we have no.
X plus 1. X plus 2.
But it's obvious that we cannot cancel out this and this, no? No? Of course, no? Because you consider this like one factor. See, we have hypothetically, I don't know, x plus 2 here. Oh, yes, we can cancel out this and this. But in this specific example, we have no common factor. No common factor. Do you see or no? Clear or confusing?
Clear.
Huh? Go ahead. No common factor. No common factor. No common factor. Do you see or no? Therefore, conclusion, we have no hole. We have no hole. In this specific example, we have no something like that. Okay? I suppose you understand very well that when you have, for example, x plus 2 divided by, I don't know, 3x plus 5, we cannot cancel out this x and this x, right? Yes or no? Okay? We cancel out factors. Factor is any expression divided by itself. So when it's the same expression, you cancel out. Because you suppose que the answer is 1. Okay? Oh. What's going on? Okay. Thank you. Do you see whiteboard now? Because you accidentally, I closed the section. But I open it. Are you there? Okay. What is the step 2? What is the step 2? Tell me. I need help. Come on. Following the guideline. What is the step 2? Okay. Exactly. AY NZ, que es evaluar en 0. Oh, nice. Evaluar en 0 is 4 times 0 divided by 0 square minus 4. 0 times 4 is 0 divided by negative 4 is 0. And when this situation happens, 0, 0, this is x value, okay, this guy. And this is a y value, okay, this guy. In this case, when this situation happens, when the y-intercept is 0, 0, it's because it's both. It's x-intercept and y-intercept. Maybe we have another or no, depending on the problem, x-intercept. In the x-intercept, remember the formula is f of x equal to 0. By the way, it's equivalent. P of x equal to 0. So you take the polynomial in the top. I don't care at the bottom. The bottom is not important for me. No. Because for x equal to 0. Again, divided by 4 both sides. It's obvious it's x equals 0. And the U confirmation, que 0, 0 is both. X intercept and y intercept. This is an important point. In this example, 0, 0 is important. Everyone follow me? You are lost? It's clear, confusing? Okay. What is number 4 step? Clear. What is number 4 step? Yasmin. What is number 4 step? Well, number 4 step is determine the vertical asymptote, no? To determine the vertical asymptote, you determine vertical asymptote. You take the polynomial at the bottom and you force it to be 0. What do you recommend me to do? in the original way or in the factor form? What do you recommend me? What do you recommend me? In the factory form or the original? Let me see. In the factory form, okay, I respect. Super. And the factory form is x plus 2, x minus 2. Entonces you separate using the zero factor property. You separate x plus 2 equals 0. X minus 2. And x minus 2 equals 0. X equals positive 2. Okay. And we have, in that moment, we have, okay, I don't know why, guys. In this moment, this is a moment I like so much to start the graph by hand. Of course, after I am doing by decimal, no, to confirmation everything is okay, you know, so be right. But I don't know why I like so much, at least doing one dimension part. And one dimension part, the information that we have in that moment is the 0,0 here. Okay, 0,0 is x in a set and y in a set, 0,0. And 2, 1, 2, 1, 2, positive 2, and negative 2. We have 2 very cast. This is the situation that we have so far. Very cast the 1, very cast the 2. I put a name, but not necessarily name. Everyone follow me? And little by little, we can track the graph. What is step number 5? What is step number 5? Horizontal asymptote. Very well. Now remember, we are doing the analysis of the degree. Degree analysis. Degree analysis. Okay, I come back at the beginning. The beginning is 4x over x squared minus 4. Degree of the polynomial at the top is 1. Degree of the polynomial at the bottom is 2. Okay, so I ask myself, we have or we have no horizontal? Yes, no. Question, we have or no? Answer me. Yes or no? No. Everyone is agreeing no? Be careful. Yes, no, yes, no. Okay, be careful. Because horizontal have two cases, regular and special. Regular, when the degree is the same, I agree. And special, when the degree of the denominator is bigger than. Entonces es special, because degree is 2. Entonces, the answer is yes. Yes, we have, pero special. Very well. Special. Special means y0. Okay. And y0 is here, look at that. Pam, 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 pam. This is my, in blue color, horizontal asymptote at y equals 0. And remember, don't forget, when you discover that we have horizontal, we need to investigate if the graph crossed or no. This is mandatory, guy. Crossed the horizontal. Bueno, I can see que cross en 0,0, no? Because the horizontal asymptote is the line, the horizontal line y equals 0, that is exactly coincident with the x-axis. So they are perfect coincident, at least crossed in 0,0. However, let me try to prove. How you prove? Well, you take the original equation. You take the original equation, que is this, and you enforce it to be equal the value of the horizontal, que is 0. This equation I solved before. I solved it before when we are doing the x-intercept. Okay, entonces es the same thing. Okay, entonces we have the famous point when our graph, our curve crosses the horizontal es 0,0. Okay, perfect. Super. Entonces now we spend time to test symmetry. Number 6, test symmetry. It's super easy because the only thing I did symmetry is reflection. You are doing reflection, but reflection are about the x-axis. So you replace x for negative x. So 4 times negative x divided by negative x squared minus 4. I did the reflection. Minus 4x divided by, and so minus x squared is positive, minus 4. And we compare this expression and this expression. What do you think? Is even? Is odd? Or is neither? What do you think? Is even? Is odd? Or is neither? Opinion, guys, opinion. Is even? No, I totally disagree. Because even is when you make a reflection and the function stays the same, doesn't change. This is even. However, in our specific problem, no, we have a minus here, right? When you are doing the reflection and it's totally opposite sign, it's odd. And even at odd, both are special functions. The regular, the ordinary function is neither when you do not satisfy this condition. Entonces, one more time, I ask you, ¿es even, es odd, o es neither? Opinion. Es neither. Randy say es neither. Randy, everyone agree or disagree que es neither? No, es odd. Okay, look. It's odd. It's odd. It's odd. It's odd. Why is odd? Because look at that. This minus, okay, this minus we can write like that. 4x over x squared minus 4. That these and these are equivalent. It's the same thing. You put a negative in the top and the front. Now this expression is identical to this expression. What is the only difference? The minus in the front is exactly this minus. It's odd. That means that the negative part is opposite sign to the positive part. Okay, entonces intuition, okay. Do you see, would you neither look like, how would a neither look like? Neither is when you make the reflection. I promise you see another example. You make a reflection and the expression is completely different to the original. No equal to in brother, even. An opposite sign is a family. When it's completely crazy, when the sign is completely different, it's neither. Entonces, what is the conclusion? Well, the conclusion is that when you perform the graph, the graph is, suppose that this is the y-axis. Look. The graph is, suppose that I am, for example, doing that part, if we discover using additional point get negative, that part, and that part is exactly the same but positive. This is a typical odd function. And the other branch maybe is a vertical asymptote, it's positive, and this is negative. Do you see the idea for the symmetry? Pero bueno, professor, pero where come from this? No. This is the last moment. I need to select additional point, no? Additional point. Okay, guys, I want to stop. We continue next time. to this because I have another class. I need to prepare the next class. Okay, thank you so much for your attention. Okay, let me ask something. Okay, no. But stay 1 second. Everyone, I suppose que saw your grade and the test one on paper and online. I posted in Blackboard. Do you see, right? Any problem, any discrepancy, anything that you don't understand, you can communicate with me by email. Professor, could you explain me? I explain, right? Because I have in detail here your mistake, or I am happy with this class. I am happy. Okay, thank you so much.